All right, today we're going to dive into one of the most elegant and frankly beautiful algorithms in all of computer science, Kadane's algorithm. It's an absolutely brilliant solution to a problem that pops up more than you'd think, and the story behind it? Well, it's a perfect example of a true flash of genius.
So you get a feel for this, let's put ourselves in a real-world scenario. Let's say you're a stock trader. You've got this long list of daily profits and losses, some good days, some bad. Your job is to find the single, unbroken stretch of days that made the most money. And here's the catch. You can't just cherry-pick the good days, they have to be consecutive. So where do you even start?
Turns out this stock market puzzle has an official name in the world of computer science. It's called the maximum subarray problem. You're given an array of numbers, and your mission is to find that one continuous slice, that subarray, that adds up to the biggest possible number. It's a really fundamental problem, and how you solve it says a lot about how you think.
Okay, so how would you even begin to tackle this? Well, the first thing most of us would probably think of is what's called the brute force method. It's exactly what it sounds like, a grind. It's the slow, obvious path. And understanding why it's so slow is the key to appreciating just how clever the better way is.
And this slide really just lays it all out. The brute force way has a time complexity of O(n squared, which is a fancy way of saying that as your list of numbers gets longer, the time it takes to find the answer explodes. It gets exponentially slower. But then you look at Kadane's. It's O(n). That means it just takes one single, clean pass through the data. It's the difference between crawling and flying. I mean, the logic here is pretty simple, right? You literally check everything. You start at the first number and you add up every possible subarray that starts there. Then you move to the second number and do it all over again, and again, and again. You can see how this gets out of hand really fast. For a huge list of stock data, this is just not going to work.
And this is where the story gets really good. This massive inefficiency was just begging for a better way, for a shortcut. The world needed a hero, and that search for a faster method led to this moment of pure insight, a brilliant shortcut that completely changed the game.
So let's rewind a bit. This whole thing kicked off back in 1977, originally for recognizing patterns in images, of all things. People started chipping away at it, finding clever but still kind of complex solutions. But then, around 1979, a statistician named Kadane happens to be at a seminar at Carnegie Mellon where someone is presenting this very problem.
And this is the absolutely legendary part of the story. After just hearing the problem described, Kadane reportedly came up with this super-fast single-pass O(n) solution right there on the spot, in under a minute. Can you imagine? It was this incredible flash of genius that just blew everyone away.
So what was it? What was this incredible insight that let him solve it so fast when others were struggling? All right, let's unpack that aha moment and see the beautifully simple logic that makes this whole thing tick.
Here it is, the entire foundation of the algorithm. The absolute key is this: if you're adding up numbers and your running total ever drops below 0, that whole chunk you've been tracking is now toxic. It's dead weight. It can only ever drag down the sum of any future subarray that includes it, so the smartest thing to do? Just drop it. Forget about it. Reset your sum to 0 and start fresh with the next number.
Okay, let's actually see this in action. We just need two variables: current sum, which tracks the subarray we're building right now, and max sum, which is like our all-time high score. We start with the first number, -2. Our current sum becomes -2, which is our best so far, so max sum is also -2. Now, here's the magic. Since our current sum is negative, it can't possibly help us, so bam, we drop it. Reset current sum back to 0.
All right, next up is 1. We add it to our fresh start, so current sum is now 1. That's better than -2, so we have a new champion. Max sum is now 1. Then we hit -3. That drags our current sum down to -2. And we're back in the red. We're carrying dead weight again. So what do? We reset. Current sum goes back to 0.
Okay, now we're talking. We get to the number 4. Our current sum jumps to 4, which is a new record, so max sum becomes 4. Next is -1, which dips our sum to 3. But hey, it's still positive, so we keep going. Then comes a 2. Boom, our current sum is 5, another new record. Then a 1 takes us to a current sum of 6. That's our new champion.
After passing over the last couple numbers, our algorithm is done. And just like that, we have our answer. The maximum possible sum from a continuous subarray is 6, all found in one simple, incredibly efficient pass. So clean.
But, it's never that simple, is it? Even the most beautiful ideas can have a tiny little flaw if you don't account for tricky situations or what we call edge cases. So what happens when every single day is a loss? So check out this array, all negative numbers. If we just follow our reset to 0 rule, what happens? The current sum will always be negative, so we'll just keep resetting it to 0. The algorithm would finish and tell us the max sum is 0. But that's wrong, isn't it? The best you can possibly do with this list is to just take the single best day, which is -1. Our simple logic just failed.
So how do we fix this? It's a really subtle but super powerful change in how we think. Instead of just resetting when the sum is negative, we ask a smarter question at every single step. We force a choice. Is it better to extend our current streak by adding this new number? Or should we ditch the old streak entirely and start a brand new one with just this current number? By always taking the max of those two options, the algorithm handles the all-negative case perfectly. It's a small change, but it makes the algorithm truly robust.
Okay, so we've got this awesome, super efficient, robust algorithm. But you might be thinking, cool, but is this just some neat party trick for a job interview? Well, no. It turns out this core idea of finding the best chunk of something shows up all over the place.
I mean, think about it. In computer vision, a version of this logic can be used to find the brightest region in a picture. In biology and genomics, researchers use it to pinpoint important segments in long sequences of DNA. And of course, it takes us right back where we started, finding that one golden trading period for a stock.
And look, if you're in tech or you're trying to get into tech, you absolutely need to know this one. It's a classic interview question at all the big names, Google, Amazon, you name it. And the reason why is that it's not about memorizing code. It's about showing that you can think your way from a clunky, brute force solution to a really simple, elegant one. It's a true classic for a reason.
So, we've totally nailed this problem in one dimension, right? A straight line of numbers. But let's not forget where this whole journey began. Ulf Greneder's original challenge wasn't a line. It was a 2D grid. The goal was to find the rectangle with the biggest sum. So, how would you do that? How could you take Kadane's brilliant one-pass idea and make it work in 2 dimensions? Now that is a fun puzzle to chew on.